let's review inverses and how I find them. So the ordered pair AB is in a relation if and only if the ordered pair BA is in the inverse relation, because with inverses, x becomes y becomes x. So if we are given the function f of x equals x cubed plus 1, let's go ahead and use that rule to fill in our table of values here. So I'm going to take each x value, plug it in, cube it, and then add 1. So negative 2 cubed is negative 8, plus 1 gives me negative 7. Negative 1 cubed is negative 1, plus 1 gives me 0. 0 cubed is 0, plus 1 is 1. 1 cubed is 1, plus 1 is 2. 2 cubed is 8, plus 1 is 9. And so that is the function that we have already graphed for you here. The cubic function is provided for you. Now we're going to swap the x and y values to have the coordinates for the inverse. So instead of negative 2, negative 7, it's negative 7, negative 2, 0, negative 1, 1, 0, 2, 1, 9, 2. And this is a very quick way to find the graph of the inverse function. We just swap the x and y coordinates and plot those new coordinate pairs. So if I go over to negative 7 down to negative 2, at 0, I'm down at negative 1, 1, 0, 2, 1, and then 9, 2. And then I can sketch in my cube root graph. All right, so the inverse of relation is a function if and only if each horizontal line intersects the graph of the original relation in at most one point. So if we look at a quadratic function, it is not going to pass this test. It passes the vertical line test, so a quadratic is definitely a function. But if we try the horizontal line test, it fails. The horizontal line touches a parabola in two different spots. So that tells us then that the inverse is not a function. And so that means it is not a one-to-one function. To be a one-to-one function, it means it would pass both the vertical and the horizontal line test, and both the original and the inverse would be functions. With the even polynomials, like the quadratic pictured here, if you remember when we found their inverses in Honors Algebra 2, we would restrict the domain so that its inverse would be a function, and we would only include half of the graph so that it would pass the test and be a function. We are going to now practice using the vertical line test to determine if we have a function in the original, and then we'll use the horizontal line test to determine if the function is one-to-one. So if we look at this first one, we have some kind of reciprocal function here. We're seeing, a vertical asymptote. And if we draw vertical lines, it's going to pass the vertical line test. So it is a function. But let me get rid of all those vertical lines I drew on there. If I would draw a horizontal line, I can touch two spots. So it is not a one-to-one function. Because it's failing that horizontal line test. So the original is a function, its inverse would not be a function. If we take a look at number 3, it fails the vertical line test. So this is not a function, and therefore it is also not one-to-one. All right, so a reminder how we verify inverses. The inverse composition rule states that a function f and g are inverses if and only if f of g of x equals x and g of f of x equals x. So to algebraically verify whether things are inverses, we compose them. That's one of the applications of composition of functions. If when we compose, we fully simplify and all we end up with is x, the original input, then we know if that works in both directions, they are definitely each other's inverse functions. They cancel out all the operations. So let me try f of g of x first. If that one works, then I'll go on to try g of f of x. If this one fails, there's no need to go any further. I've already shown that they are not each other's inverse. So I'm going to take the g of x function, which is the cube root of x minus 1, and put it in place of the x in f of x. So I took this whole thing and put it in place of that x. So I have to raise it to the third power and then add 1. So we know that cube and cube root are inverses, opposite operations that cancel out. So we'll just be left with the radicand underneath, which is x minus 1, and then we still have that plus 1. So minus 1 plus 1 cancels to just give you x. So it works in that direction. Now we have to check it in the other direction. So g of f of x. So this time I am taking the f of x function and putting it in place of the x here. So we've got the cube root of x cubed plus 1, and then we have the minus 1 behind it. So if we go ahead and simplify those constants under the cube root, 1 minus 1 would be 0, so we'd just be left with the x cubed underneath the cube root. And again, these are inverse operations that undo each other. So we're just left with x, and since both directions, f of g of x and g of f of x, simplified to equal x, they are definitely inverses. If either simplified to equal anything besides x, 2x, x plus 7, x minus 4, then we would say no. They both have to completely simplify down to just x. All right, so let's try one with reciprocal functions here. So f of g of x. So every place there's an x, so both of these x's have to get replaced with this entire fraction. So we'll have 2x plus 3 over x minus 1 plus 3 over 2x plus 3 over x minus 1 minus the 2. So we've got to use some skills that we learned from Honors Algebra 2 about complex fractions. We don't want like a fraction in a fraction. So I'm going to fraction bust my common denominator. They both have the denominator x minus 1. So I'm going to multiply top and bottom of this fraction by x minus 1. So when we take x minus 1 and multiply it by this fraction, it's going to cancel out that denominator. And so I'll just be left with a 2x plus 3. But then I also have to take the 3 and multiply it by the x minus 1. So I'm distributing this times this fraction. It's canceling out the denominator, and I'm just left with 2x plus 3. But then I also have to multiply it by the 3, and so I'm going to have to distribute there in a minute. Let's do the denominator. Same thing. Take this times both of these terms. So when I take it times this fraction, it's going to cancel out that denominator and just leave me with the 2x plus 3. But I still have to multiply the 2 by the x minus 1. And I know it's enticing to see these and think, oh, can I just divide those out? But we cannot, because they are part of a sum or part of a difference. You can only divide out things that are part of a product. So because here I was multiplying this by this fraction, then I can divide out. Division undoes multiplication. Division is never the opposite of adding or subtracting. So I have to just simplify by distributing. So we have 2x plus 3 plus 3x minus 1. Or sorry, distribute. Not minus 1, minus 3. Distributing the negative 2 in the bottom. So you'll still have your 2x plus 3, but now you have minus 2x minus 2, or plus 2. Negative times a negative. And so if we combine like terms, we have 5x, because 3 minus 3 is 0. And then in the bottom, 2x minus 2x is 0. We have 3 plus 2, which is 5. We know 5 divided by 5 is 1. And so we just get x. All right, so it worked that direction. So now I've got to check the other direction. I'm just going to shrink this down a little bit so I've got enough room here. to do it all over again, only this time g of f of x. Okay, so this time I have to put the x plus 3 over x minus 2 into the g of x function. So I almost forgot I have to multiply that by 2. So let me slide it over a minute. Put my 2 in front of it, plus 3. And then in the bottom, x plus 3, x minus 2, minus 1. So again, I'm going to fraction bust. I'm going to multiply top and bottom by that little denominator that I need to cancel out so that I don't have a fraction in a fraction. So I have to take this times this first term and the second term. When I take this times this first term, it's just going to cancel out the denominator, and I'll just have the 2 times x plus 3. But then I have to multiply the 3 by the x minus 2. In the bottom, again, when I take this times this, it's going to cancel out. I'll have the x plus 3. And then I have to take the negative 1 times the x minus 2. So now I've got to distribute and combine like terms here. Again, I can't cancel anything out because I have sums and differences, and division cannot undo adding or subtracting. Okay, so in the top we have 5x, 6 and negative 6 add to 0. In the bottom, x minus x is 0, 3 plus 2 is 5, 5 divided by 5 is 1, so we just have x. So both ways it's simplified down to x, so we get to say yes, they are inverse functions. Finding inverses algebraically. So our first step, we're going to swap f of x with y if it's written in function notation. Then we're going to switch the x and the y, and we will resolve for y. So in number 6, we'll get rid of our g of x, which is the same as y. Replace it with just a normal y equals. And now we will swap the x and the y. So we have x equals the square root of y plus 5. And I start working my way towards that y. I want to get the y by itself. So first I need to undo the square root, and the opposite of that is just square. So I will square both sides and have x squared equals the radicand, y plus 5. So then we'll subtract the 5, and we will have our inverse function. We will have x squared minus 5 equals y. Reminder that to signify it's the inverse, we use the notation of the negative 1 exponent. Really, we should go back to function notation, though, and say g inverse of x equals x squared minus 5. Number 7. So again, get rid of the f of x, replace it with y equals. And then we'll swap the x and the y. I can add the 2 to move it over because now I'm starting to solve for y. And then the trick I'm going to use here is to essentially cross multiply. I'll remind myself that x plus 2 could be thought of as a fraction with a denominator of 1. And once I have fraction equals fraction, that's called a proportion, and we're allowed to cross multiply and solve. We know the cross products equal one another. Or you could just think of it as multiplying both sides of the equation by y plus 6 to fraction bust. At any rate, you would end up with this. The product of x plus 2 times y plus 6 equals the product of 1 times 1, which would just be 1. Since I'm trying to solve for y, I'm now going to divide by the x plus 2. So that we'll have y plus 6 equals 1 divided by x plus 2. We'll finish it off. We will subtract the 6 to the other side. And now y is all by itself, so that's our inverse. So we can put the little negative 1 there, but again, we should really go back to function notation in the end and say f inverse of x equals 1 divided by x plus 2 minus 6. All right, so number 8, again, replace the f of x with y. And then we'll swap the x and the y. So we'll have x equals 3y plus 5. divided by y plus 1. So every place there's an x, I have to put y. All right, so now we're going to solve for y. So we're going to use that proportion trick. We're going to think of it as x over 1. So we've got fraction equals a fraction, and we can cross multiply. When we cross multiply, our cross products have to equal one another. So x times y plus 1 has to equal 1 times the 3y plus 5. Or again, you could think of it as just fraction busting, multiplying both sides by the y plus 1 to clear it out. We have to distribute this time because we have a y on both sides of the equal sign, and so I'm got to be able to move them onto the same side with addition and subtraction, which means I need to distribute. So we get xy plus x equals the 3y plus 5. And so now I'm going to subtract the 3y to the left-hand side so that all my y terms are on the left, and I'm going to subtract that x to the right side. So we have xy minus 3y will equal 5 minus x, or negative x plus 5, either one. And now on the left, I'm going to factor. I see both terms have a y, so that's my greatest common factor. I can factor that out. And now we can divide both sides by the x minus 3 to get y all by itself. So we have y equals 5 minus x over x minus 3. Since y is all by itself, that's the inverse. We can show that with the little negative 1 exponent, or back in function notation, f inverse of x will equal 5 minus x over x minus 3. And if you would divide that all by negative 1, that would be fine as well if you had x minus 5 over 3 minus x, or you could write the top as negative x plus 5. Any of that would all be the same. And that's how we find an inverse function from the equation. All right, we're going to review composition of functions and talk about something called decomposition of functions. Just remember that the composition of functions is the successive application of the functions in a specific order. Given two functions f and g, the composite function f of g is defined by f of g of x. The domain of f of g is the set of elements x in the domain of g such that g of x is in the domain of f. Reminder that this little open symbol here, that's the symbol that represents composition. So this means f composed with g. It's not multiplication because it's not filled in. So that little open circle means we are taking g and inserting it inside of f. If we want f of g of x, we're going to take the g of x function and insert it in f in place of the x. So it would look like this. All of this would go in place of that x. So where the x is, we leave a blank spot, and then we replace it with the other function. So it was originally just x minus 3. In place of the x, we put the whole function 2x squared minus 1. And then if we combine like terms, we have 2x squared minus 4, as shown here. Now if we want to compose the opposite direction, so if we want g of f of x, we're going to take that f of x function, x minus 3, and insert it in place of the x in g of x. So they show that here. We took x minus 3, put it in place of the x, so it's now to the second power because x was being squared. So we have to take care of that first. Reminder that if you want to square a binomial, you have to do x minus 3 times x minus 3, and use FOIL or box to get the x squared. Minus 3x gives us that negative 6x, and then the plus 9. So next we would have to distribute the 2 and get 2x squared minus 12x plus 18. Then we'll combine like terms here to get this final simplified polynomial, 2x squared minus 12x plus 17. So function composition is not commutative, order matters. F of g of x is very different than g of f of x. All right, so we have 3 example functions here, f, g, and h, and we're going to go through and do some different compositions. Number 1 says f of g of x. So I'm going to write down function f, but where the x is, I just leave a blank spot, because in place of it, I have to put the g of x function. And the g of x function is this one here, so all of this is going to go in place of those parentheses. So then I can distribute. We'll have 4x squared minus 12x plus 16. And we still have the plus 1 that was on the outside. So we'll have 4x squared minus 12x plus 17. Nope. I'm sorry. I just checked my work. I accidentally changed the sign there. That should be minus 12x minus 16. So the negative 16 plus 1, we'll have negative 15 here. All right, so f of g of x should be 4x squared minus 12x minus 15. All right, number 2 is the opposite. It says g of f of x. So this time I'm going to write down function g. But again, any place there's an x, I'm going to leave a blank spot because we'll be substituting in place of it the f of x function. And f of x is 4x plus 1. So 4x plus 1 goes everywhere there was an x. And so the g of x function had two x's. The first x that was being squared, and then minus 3 times x. So 4x plus 1 went into both positions. So if we square that binomial, we would get 16x squared plus 8x plus 1. Again, remember you would have to write it out 2 times and use FOIL or distributive property. We distribute here, we get negative 12x minus 3, and we still have the minus 4 that was on the outside. So we get 16x squared minus 4x. 1 minus 3 would be negative 2, take away 4 more is negative 6. So g of f of x is 16x squared minus 4x minus 6. All right, next we have f of h of x. So again, I'll write down function f, but where the x is, I leave a blank spot. And in place of that, I put h of x. So instead of 4 times x plus 1, we have 4 times the quantity x squared minus 9 plus 1. So we get 4x squared minus 36 plus 1. So we'll have 4x squared minus 35. All right, number 4 says h of f of x, so the opposite. So I'll write down the h function. You always start with the first one is the one that you're inserting into, and then the inside is what we're putting in to replace the x's. So I start by writing down this function, but I don't write the x, I just leave a blank spot. So the input has to be squared, and then I have to subtract 9, and the input we're supposed to use is f of x. So I'm going to bring this f of x function and put it where that x was. And then I simplify. So again, we've got the binomial squared, so we'll get 16x squared plus 8x plus 1 minus 9. And so if we combine like terms, we get 16x squared plus 8x minus 8. All right, we can also do this with actual numbers. So if we're given a number, we can actually go ahead and evaluate this, and then we'll insert it into G. So we can do some simplifying inside before we actually insert it into G. So I'm going to first evaluate h of negative 2. So function h says to take that input, square it, and subtract 9. So I'd get 4 minus 9, which would be negative 5. So when they say g of h of negative 2, well, we just figured out that h of negative 2 was negative 5. So what they really mean is find g of negative 5. So function g says to take the input, square it, subtract from it 3 times the input, and then subtract 4. So negative 5 squared would be 25. Negative 3 times negative 5 gives us positive 15 minus 4. So 25 and 15 gives us 40. Take away 4 gives us 36. So g of h of negative 2 equals 36. All right, next one says f of 5. So first we'll figure out what f of 5 is, and then we'll have to insert that value back into the f function again. So function f says 4 times the input, which is 5, plus 1. So 4 times 5 is 20, plus 1 gives us 21. So then f of 5, well, we just figured out f of 5 was 21, so it's really f of 21. And again, function f says 4 times that input plus 1. So we'll have 84 plus 1, and we'll get 85. All right, so that's composition of functions, where we're inserting one function inside of another. The opposite of that is called decomposing, or decomposition of functions. So decomposing a function means breaking down a composite function into two simpler functions that, when composed, result in the original function. This process involves identifying the inner and outer functions of the composite function. For each function h, find the functions f and g such that h of x would equal f of g of x. So first of all, like most things in math, there are options. And in this case, there's multiple things that could be considered the right answer. So we may not all think of the same way to break them down, but we're trying to figure out what could f of x and g of x be, so that if I take this function and insert it into this via composition, my answer ends up being h of x. And so the first thing I notice is that in both of these, we have this x plus 1. So that feels to me like that was what was inserted into the function. So I'm going to allow that to be my g of x function. And so if we replace that, if we take that out and just replace it with x's, then I would have the function x squared minus 3x plus 4. So that would be a possible decomposition, because if I would find f of g of x, like they're saying here, h of x equals, I would have to take the x plus 1 and plug it here and here, and I would end up with this equation. All right, number 8. So we have the square root of x cubed plus 1. And again, there are options. There are multiple things that you could put here. I'm going to choose to view this as, okay, my input was this. If g of x was x cubed plus 1, and I inserted that into f of x, well, if I replace it with just the x, that the square root of x then could be f of x. Because if I would do f of g of x, I would take all of this and put it in place of the x, and so I'd have the square root of x cubed plus 1. Another possibility would be you could just have the x cubed here for g of x, and then you could make f of x the square root of x plus 1. That would also work out. All right, number 9. Again, I'm going to view this expression under the square root as my g of x, the thing that was inserted. And so if I think about replacing that with x, I would just have 5 divided by the square root of x. So f of g of x, I would take x plus 12, put it in place of the x here, and I would wind up with 5 divided by the square root of x plus 12. For number 10, we could view, again, the inside here as the g of x, x plus 8. And so then f of x would just be 2 times the absolute value of x. Because whatever I'm taking out as g of x, that's where just a normal x would go. Because when we do the composition, we would take this and put it in place of the x. And so if I put x plus 8 in place of x, then we'll have 2 times the absolute value of x. So perhaps you thought of other ways of doing this, but that's at least one way to do it.